Assalamu alaikum everyone. I want to show how we can represent a signal as a combination of even and odd signals. Just for a recap first, what even and odd signals are. So even signal is defined with this mathematical relation that xt is equal to x of minus t, means that a signal xt will be called even if its reflected part also looks the same, means even if we reflect it, the signal will still remain the same, or its waveform will remain the same. For example, this signal, if we reflect it on the time axis or we flip it, it will still look the same. You see, we flipped it from positive side to the left to the negative side on the time axis, but still it looks the same. So it is called as an even signal. This is another example of an even signal. And the odd signals are such that when the signal is reflected, it is not equal to, or it does not look same as the original signal, but if we flip the reflected signal vertically, then it looks the same as the original signal. How? Let us see this signal. If we reflect it on the time axis, it will look different. See, it is the different signal than the original one. Now if we flip it on the vertical axis like this, it will look exactly the same as the original signal. Such signals are called as odd signals. Here you have to note this point, that in the bracket where it is mentioned t in both of these, that t refers to the value on the time axis. Okay, so minus t means that it is reflected on time axis, and the x outside the bracket represents the value on vertical axis. Okay, and the negative sign with it means that it is reflected or flipped on the vertical axis. So there is another example for odd signal. Okay, now let's see how we can represent a signal which is neither even nor odd signal as a combination of even and odd signals. So signals can be represented as sum of even and odd components. For example, this signal xt can be represented as the sum of its even component and odd component. Here xet is the even component, while xot is the odd component of the signal xt, and these are the formulas to find xe and xo. These are very simple. xe is equal to half or 1/2 times the sum of the original signal and its reflected variant, right? While xot or the odd component is 1/2 times the original signal minus its reflected variant, right? Very simple. Now let's see an example. So in this example, you are required to represent this signal xt as a combination of even and odd signal. Okay, so according to the definition of this signal, xt is equal to 1 for the region between 0 and 1, and it is 0 otherwise. Okay, so first we see the given signal. Okay, then we reflect it. In order to find its reflected signal, we'll do it like this. So you remember, the reflected signal has minus t, means that the values of t will be reflected, or those will turn from positive to negative. So the original one is from 0 to 1, so the reflected one will be from -1 to 0, right? The values of t in the original one range from 0 to 1, while in the reflected one they will range from -1 to 0. Okay, clear? Now let us find out the even component and odd components. So the even component can be computed using the formula that we just saw before. So here XET, or the even component, is equal to 1 over 2 XT plus its reflected variance. So we can write this function as this. So XET is equal to 1 over 2, and there are three rows now. As you can see, the top row is XT, okay, and the second row is the reflected variance X minus T, because we are adding both of them. Both have different regions, that is why we will write them separately. And the next is 0. It will remain 0 for all other regions. Now we multiply 1 over 2 inside the bracket with 1 only, the values, the magnitude of xt. So from 1 we get our value 1 over 2 and 1 over 2. So similarly we can compute our odd component of the signal like this. So there is only one difference. In the even component we perform the sum of original with its reflected variant. Here we perform the difference or subtraction. So the reflected variant is subtracted from the original signal. This one we can write like this. So you notice the difference is there is minus 1 here. So this one is from the original signal and this one is from the reflected signal, but the negative sign with 1 is because of the subtraction, because we are subtracting it from the original one. That is why we will use negative sign with it. After that we multiply 1 over 2 inside the bracket, and our odd component is XOT, 1 over 2 in the region from where T ranges from 0 to 1, and minus 1 over 2 in the region of T minus 1 to 0 and 0 otherwise. Now let's plot them. So this is how we can sketch them. The given signal is like this. So it has one magnitude between 0 and 1 and 0 otherwise, and the reflected signal is like this. So it flips from 0 to 1 to 0 to minus 1, and the even component can be represented like this because it has value 1 over 2 between 0 to 1, and it has 1 over 2 value between 0 and minus 1 also, and 0 otherwise. And the odd component can be represented like this. It has 1 over 2 value between 0 and 1, and minus 1 over 2 between 0 and minus 1. So this is how you can represent a signal as a combination of even and odd signals, and after that this is how you can sketch them also.